Okay, so yeah, so this is the result for Haar measure. So Haar measure, so firstly it is normalized. It is a unique measure, satisfies its properties. Firstly, it is normalized, and secondly, it satisfies certain symmetries that suppose you integrate the function, but you're making a change of variable using making a change of variable for this function, replacing h to h times g, or g times h, or h inverse. Yeah. And then this integration is completely invariant. Yeah. So this is property of Haar measure, and these properties are useful in many calculations. Okay, so now this is a very brief introduction for Haar measure, and for if you want to know some details about Haar measure, you can just Google it. You can find a lot of lecture notes about Haar measure. Okay. So now, what is the property? So now let's look into this Hilbert space, and it will be enough. Well, we should know a lot about Hilbert space if we can find a basis, a convenient basis of this Hilbert space, right? And well, once we understand this Hilbert space, and we should be able to understand this Hilbert space, because this larger Hilbert space on the entire lattice is just many copies of this, many copies of the same Hilbert space. So let's look at the Hilbert space of a single copy of SU2, so we can find so-called orthonormal basis, well, orthogonal basis, more precisely. Orthogonal basis in this Hilbert space, L2 SU2. Okay, and the basis is called Wigner D function. Wigner D function. Wigner D function, or Wigner, the matrix element of Wigner D matrix. Matrix elements, D functions, matrix elements of Wigner D matrix. So yeah, well, reference for this is you can check out Wikipedia, and there's a very detailed discussion about Wigner D matrix in Wikipedia. Or I'm probably in your quantum mechanics class, you may have also learned a little bit about Wigner D matrix when you learn angular momentums. You can just check out Wikipedia about Wigner D matrix. So that will be enough to learn Wigner D matrix. And what exactly is Wigner D matrix? So here, well, these are D functions, and what are those D functions? So those D functions I will call, because I want to follow the convention of book by Thomas Tiemann. So I try to use the same notation. So over there, he called it pi, but this pi, so it has three labels, J, M, and N. Okay, and it's a function. Clearly, it's function of H. H belongs to SU2. Yeah, and this is just the Wigner D function, usually in standard convention. Standard convention is called D, J, M, N as a function of H. Okay, and so here J is 0, 1/2, 1, 3/2, and so on. So J is just spin. J is a spin. And here M and N, they are magnetic quantum numbers. So magnetic quantum numbers. in quantum mechanics. So m and n, they are just magnetic quantum numbers in quantum mechanics. So m and n, they are integers. Well, n equals to from minus j plus 1 to j minus 1 and j. So they are standard magnetic quantum numbers. And so what are exactly this d, j, and n? So this is defined to be, well, it's dj of h, and usually the Wigner D matrix, D function is a function of alpha, beta, and gamma, all the angles. So this is defined to be j and m. So this is I write an inner product in quantum mechanics. So this bracket is not the bracket of the Hilbert space here. This is a quantum mechanics inner product. J3 e to the minus I beta J2 minus I gamma J3 J. So this is in quantum mechanics. So this D matrix, well, so here why we call it D matrix, because if we fix J, so D is it has two indices m and n, so this is a matrix in the spin J Hilbert space in quantum mechanics, right? So here this D matrix. So here from this formula you can also see this D m n is kind of matrix element. And this is this rotation operator. You can see the relation between this operator and the holonomy, which is SU2. See, well, our parameterization of holonomy is this. And the rotation matrix, you just replace those taus by angular momentum operator J. So it is in representation, in the language of representation, this is just the representation of H in spin J Hilbert space, in spin J representation space. Okay. All right, so this is called Wigner D matrix because, and it is a function of alpha beta angle, alpha beta and gamma. They are all the angles, and it's a matrix element of this rotation operator in the basis in quantum mechanics using the basis of Jm and Jn. They are basis in the spin J Hilbert space, what we call Vj. This is the SU2 spin J irreducible representations. Irreducible representation. Okay, so this is clearly if you fix m and n and j, it is a function of alpha, beta, and gamma parameterized group, SU2 group. So it is a function on SU2 group. So you can see that it is a function labeled by 3 parameters, j, m, and n. Okay. And moreover, you have orthogonality for this d function. If you use power measure to integrate ij and n h complex conjugate ij prime and prime n prime h. The result is 1 over 2j plus 1 delta j prime. Okay, so they are orthogonal bases. They are orthogonal. If you have different j's and different m and different n's, and the result or the integration give you delta. They have they give you just 0. They are, if you have different j, different m, or different n, they are orthogonal in the L2 inner product. So this is just the L2 inner product of the Hilbert space. So so now we can see that is pi j mn for all j and half integers. C half. Also containing 0. C plus half union 0 and n well, equals to minus j plus j. Okay, and is a also orthogonal basis. Orthogonal basis in the Hilbert space L2 SU2. Okay, so we find the basis, and for any wave function, well, this is not yet a wave function because it's only dependent on a single holonomy. Yeah, well, we can still call it a wave function, but the special wave function only depends on single holonomy. Then this f of h can be expanded by using pi. And f j and n pi j and n h. Yeah, so for any wave function in this Hilbert space, it can be written as a linear combination of bases. Here you have sum over all the j and m and n. So here f, j, and they are just complex coefficients. Okay, so this is the basis of the Hilbert space, and now you can you just make many copies of the same Hilbert space, and you can generalize it to the entire Hilbert space. So you can define orthogonal basis in the entire Hilbert space. Basis in H0, you just multiply, make a product of all those pi's. J-E. So here, well, because different edge has different degree of freedom, and you have to label all the indices in terms of E. And HE. Just simply make a product of all the edges, and these bases, well, in Thomas Tiemann's book is called T. Probably relate. Oh, anyway. It depends on well, it's labeled by J vector, M vector, and N vector, and it is a function of H vector. Well, here vector means that it's a sequence of J's, well, containing J's on all edges. So here the H vector, it is a sequence of polynomials depending on all the edges. So yeah, similarly, J, it means that JE belongs to all edges. Okay, similarly for M and N. All right, and you can just you can consider integral, the inner product of on H0. The inner product of H0 is just given by making product of the Haar metric, because they are just copies of the same Hilbert space. Inner product. Consider inner product between two bases, T conjugate, say J prime, and prime. Okay, and this is the inner product between two t's, and this integral is completely factorized, right? And because the function t is factorized in every edge, and also the integration is also factorized. And when you factorize this integral to every edges, and you just get the same integral as here. The same integral as this guy. That's this formula. Okay. And the result is again factorized to all edges. And e plus 1. And then we have delta j prime. It means that I can write it like this. And then we have delta je prime delta me prime delta e prime. Okay, it means that they are bases, right? They are orthogonal bases. So if the index are completely the same, it equals to a constant. And if they are not the same, equals to 0. And the inner product equals to 0. Okay, so this is the basis of the entire Hilbert space. And again, similarly for any wave function belongs to the entire belongs to big Hilbert space. This large Hilbert space have as a function of all holonomies, it's a linear combination of those bases. Sum over all j, m, and n's have j, m, n, p, j, m. Okay, so this is this is the result of those Hilbert space, the structure of the Hilbert space. And we find also normal basis of those Hilbert spaces. Okay, so now, however, those wave functions, they are not yet gauge invariant. Okay, so we consider those Hilbert spaces just a product of SU2 Hilbert spaces over all the edges, and it means an arbitrary function of all the holonomies. But we know that holonomy is not gauge invariant, so we have to consider, because we are doing a gauge theory, we have to consider some gauge invariant as best as we can. So that's why I call it H0. It means H0. It means that it's non-gauge invariant Hilbert space, or the Hilbert space of non-gauge invariant wave functions. So here next we are going to define a Hilbert space of gauge invariant functions. Well, I think we should do it next time. So I think probably a good time to stop. Any question about this lecture? We postpone the gauge invariance next time.
I just want to confirm one concession.
Sorry?
I just want to make one concession.
Completion? You mean?
I want to make one concession, my understanding. Because actually, because holonomy because the holonomy is the element of the SO2, right? So this is why we can use the holometer. Am I right?
Sorry, I don't. So you mean completion of your Hilbert space, of the Hilbert space?
I mean, the reason why we can use the holometer is because the holonomy is the element of SO2.
The holonomy, you mean holonomy? It is also the matrix element of holonomy is also a function.
这有没说do I understand the process correctly?
Okay, so clearly it is so these functions are functions on SU2, right? Because it depends on alpha, beta, gamma.
Oh yeah.
Yeah, you can integrate them because you have the measure. You have the integration. You define the integration already. We have the integration.
Okay.
Yeah, and it is a function of holonomy, clearly because we have parameterizing holonomy using alpha, beta, and gamma.
Okay.
Holonomy belongs to SU2.
Okay. Got it.
Yeah, holonomy belongs to SU2. Okay, probably that
Okay.
solve your problem.
Oh yeah. Thank you.
Okay, any other question? Okay, if not, then see you next time.
Bye.
Bye.
Bye bye.
Okay. See you.